Hello, Chem 1A. This is Chapter 7, Lecture Video 7, and we're going to be talking about the kinetic molecular theory. This theory basically describes how gases behave under ideal conditions. Now, there are 5 points to the kinetic molecular theory, and the first one is that gases are consisting of molecules slash atoms, depending on what the gas is made up of, that are in continuous random motion. What that means is if you can kind of think of like a container, right? And we have a gas particle, it's moving in a straight line until it hits the container. Then it bounces off the wall and continues going in straight lines in random directions, though, just based off Newtonian mechanics, right? And it'll continue moving in that exact way, right? Over and over again in a straight line, in continuous random motion. The second part of the kinetic molecular theory is that the volume of gas molecules or atoms is negligible in comparison to the total volume in which the gas is contained. So this picture I've drawn, it doesn't do it justice, right? So like if we think about this, right, a container this big, we wouldn't even be able to see the gas particle. It would be just the tiniest little blip. In fact, that dot I've just drawn is way too big to even describe it. It wouldn't even be the size of one of the pixels on my screen. So they are very, very tiny in comparison to the total volume of the container. And to that point, we usually consider their volume to be negligible. And this is one of the assumptions we make when we assume that a gas is behaving ideally. The third point of the molecular theory, kinetic molecular theory, is that the attractive and repulsive forces between gas molecules and atoms is negligible. This is the second thing we typically assume when assuming a gas is behaving ideally, is that gas particles do not attract or repel each other. Think of like magnets. They definitely attract and repel each other depending on which pole is facing the magnet. That doesn't happen at all with gases. And with most liquid and solid molecules, it actually does happen. So this is a distinct difference between gases and the other physical states. Finally, average kinetic energy, the amount of energy due to motion, on average for a sample of gas, is constant as long as temperature remains unchanged. Now, that means if I have two samples of gas, doesn't matter what the substance is. If I have carbon dioxide and oxygen gas in two separate containers at exactly the same temperature, those two gas samples will have the exact same average kinetic energy because their temperatures are the same. And the second part of this is that we assume collisions are elastic. And if you've taken physics, you might know what that means. But if you haven't, you might not. Basically what an elastic collision is, let's say I have two different gas particles and they're going to collide, right? So we have them move towards each other and eventually they collide, boom, they collide with each other and then they bounce off, right? The yellow gas particle bounces off this way, the green gas particle bounces off this way, right? Well, in an elastic collision, what we assume is that there's no energy lost when the two things collide. Now, in reality, there's no such thing. In all collisions, some tiny amount of energy will be lost as heat, friction, what have you, to the surroundings. But in an elastic collision, we assume there is no energy loss when the particles collide. And that's what we're assuming about gas particles, is when they collide, there's no energy lost in the collision, and they bounce away with the same momentum as they had before the collision. The final bullet point of the kinetic molecular theory is that the average kinetic energy of a gaseous sample is directly proportional to absolute temperature. In other words, if I heat up a gas sample to a higher temperature, the average kinetic energy of that gas sample will increase. It's also valuable to kind of understand what kinetic energy is calculated for, like what's the formula for kinetic energy, and we'll get to that on the next slide because it'll have application to some of the things we're going to talk about that the kinetic molecular theory directly impacts. So one of the things that we can use the kinetic molecular theory to predict is the average speed of our gas particles and how that relates to temperature, right? So one of the things you should know as a trend is that as the temperature, absolute temperature of a gas increases, the gas molecules in that sample start moving faster. And this is due to the average kinetic energy increasing with temperature. So another thing you should be able to read is this graph, right? So it's kind of a unique graph and it's often misread. You got to really be careful about looking at what the axis titles are. So on the y-axis or on the x-axis, sorry, we have molecular speed, and on the y-axis we have number of molecules. What that means is as we get to the peak of these graphs, just because this blue peak is taller than the red peak does not mean the red gas is going slower. In fact, it's opposite. What these peaks are is where the average speed would be, right? Because this is where most of the molecules are speed-wise. And so we can kind of say that the average speed of the molecules of oxygen at 25 degrees Celsius is approximately 400 and we'll say 10 meters per second, right? Whereas the average speed of oxygen molecules at 1,000 degrees Celsius is pretty much exactly 800 meters per second. We basically take the peak and go down to the x-axis to figure out what the average speed is based on this graph. So we can kind of see that here. So to kind of think about why this is occurring this way, let's look at the actual formula for kinetic energy. So kinetic energy is equal to 1/2 mass times velocity, right? So speed, basically. And physicists would disagree with me calling velocity speed, but for intensive purposes in this class, we can kind of relate the two things. So if temperature increases kinetic energy, does temperature increase mass? No, mass is constant, right? It's conserved. So mass isn't changing when I change temperature. What has to be changing if kinetic energy is increasing with temperature? Well, that has to be the speed of the gas particles. So that's part of the reason why increasing the temperature will make the gas particles move faster, is because according to the kinetic molecular theory, increasing temperature increases the kinetic energy, and increasing temperature is not going to change the mass of the sample or the mass of the gas particle. So the only thing it can change, therefore, is the speed. So let's look at average speed versus weight. And one of the things I like to use here as an analogy is I was a track athlete in high school and in college a little bit. So average speed versus weight, I always like to think of like the differences between like a shot putter athlete and a sprinter. And if you've ever seen the Olympics, I know we kind of missed out on the Olympics this year, or in 2020, right? But if you've ever seen the Olympics, you know that the sprinters tend to be really light, small guys, tall but really thin with defined muscle mass, not big muscle mass. Whereas the shot putters and the discus throwers, these guys are huge. They're really tall guys. They got huge muscles, really big. The shot putters are going to be heavier than the sprinters. But who's going to win a race? It's going to be the sprinters. So that kind of also applies to our average speed versus weight. Molecules with larger molar mass or molecular weight tend to move much, much slower than molecules with low molecular weight or molar mass. Same thing. Molecular weight, molar mass, these are synonyms. In other words, light molecules are going to move faster, I should say, than heavy molecules. They're going to move slower. So we have actually an equation for this. However, I'm not going to have you guys using it in the class. we're just going to kind of ignore this. There is this equation out there. The problem with it is the R value that we're used to is not 0.08206 here. That's the wrong value for R. It doesn't work. Molecular weight or molar mass will have to actually be in kilograms per mole. There's some uniqueness to this equation. So I don't want you guys having to use it, so don't worry about it. We're not going to use it on the test. All right, so don't worry too much about that. However, if we look at this graph, again, we have that number of molecules on the y-axis and the molecular speed on the x. So if we want to figure out the average speed here for oxygen, we're just going to kind of scroll down here. It's, like I said, about 410 meters per second. For nitrogen, kind of go down there. That's probably about 450 meters per second. For N2, I'd say that's pretty much right on the money. That's about 500 meters per second. And for helium, we're at about 1200 meters per second. Now, if we look at molar masses, a trend begins to appear. Oxygen's molar mass is about 32 grams per mole. Nitrogen's is about 28 grams per mole. Water is about 18.02 grams per mole. And helium is about 4.00 grams per mole. So if you look at these, as you can see, the lightest weight molar mass gas particle, helium, has leaps and bounds a larger speed, average speed, than the others. And as we go from high molar mass to lower molar mass, we see the speed increase. All right, and so this is a trend you should be aware of. The last slide here is just talking about how the kinetic molecular theory actually predicts some of the properties we know about gases. For instance, the compressibility of a gas. We know gases can be compressed, and this is largely due to the container being mostly empty space. Remember that point 2 of the kinetic molecular theory states that gas particles' volume is negligible in comparison to the volume of the container it's in. This means that when we compress a gas, really we're just decreasing the amount of empty space between the particles. That's why it's possible. The pressure-volume relationship, that is an inversely proportional relationship. We need to know that pressure is actually the result of collisions of gas particles with the sides of a container. So the more collisions we have, the higher the pressure. If we have a larger volume, the frequency of our collisions in the container is going to decrease because it's a bigger space. The gas particles aren't going to collide with the container as often. This will therefore decrease the pressure. We have our temperature-volume relationship, which we know is directly proportional. To keep pressure constant in this scenario, if we increase temperature, gases are moving faster, and that means they would collide with the inside of the container more frequently. In order to keep pressure constant, the volume of the container must expand so that those collisions are still less frequent, or the same frequency as before we increase temperature. Pressure-temperature relationship is not something we actually discussed in our lecture videos. It's actually the Gay-Lussac law, which states that the pressure and temperature of a gas is directly proportional. So in a given volume, if we increase temperature, the average speed of our gas molecules increases, and so there will be more collisions in that container. And if volume is held constant, then the pressure is going to go up because of the higher collision rate. All right, so if you have any questions, please let me know. As always, you can email me, come to office hours, email me and set up a Zoom meeting. I'm always happy to help you guys.